In the description of this video is a link that will take you to a spreadsheet where you can practice flow continuity. And one of the main ideas, or the main idea, behind flow continuity is that if I have water in this cylinder and a hole drilled into it here, the rate of flow of this water moving down the cylinder has got to equal the rate of flow of the water coming out that hole. Now, some things that might affect the rate of flow is if I had a really large hole here, more water would be shooting out there every second, so the water must be going down faster here every second. And the lab that we're going to do, the link that's in the description for the spreadsheet, you want to find the diameter of that hole. And that is going to be a little challenging, but not too bad. So main idea behind rate of flow is that the number of chunks of stuff that are flowing by here every second must equal the number of chunks of stuff that flow by there every second. Okay, if I had more of these things flowing past here than were flowing past here, this pipe must be swelling up in size or something. If I had less flowing here than was flowing here, there must have been a leak somewhere. Okay, so if this is a water trough and I want to actually quantify the rate of flow, it would be just the number of chunks of water that flow by there every second. Well, a good way to measure that would be volume divided by time. So we would measure the flow or the rate of flow of the water flowing through that trough as cubic meters per second. If we were doing that in imperial units, it would be cubic feet per second, often abbreviated CFS, cubic feet per second. So volume, we can calculate the volume by area times distance. So the cross-sectional area of that trough multiplied by the distance it moves. Like if you put a tennis ball in that water and then measure how fast the tennis ball moves that distance, that's area times distance. Would also give us the volume of that chunk of stuff. Well, let's see if we can simplify this any way. Distance divided by time is the same thing as velocity. So distance divided by time would be the same thing, and times area. I'm sorry, distance divided by time times area would be the same thing as velocity times area. So if I calculate how fast that water's traveling in meters per second, and then I multiply by the cross-sectional area of that trough, I would get the same thing as cubic meters per second. So if this is one pipe here and it's tapered into a smaller area and then expanded back out, the rate of flow here, the number of chunks of stuff that go by there every second, has got to equal the rate of flow there. So the cross-sectional area of this tube multiplied by the velocity must equal the cross-sectional area of the tube here multiplied by the velocity. So basically, because it tapered from a larger area to a smaller area, the fluid must be moving faster through that smaller cross-sectional area to get the same quantity of water flowing by every second. All right, so that's our big equation. The rate of flow is going to equal the rate of flow. And this is just the area in one circumstance and the velocity in one circumstance. Area in the other and the velocity in the other. All right, that's the equation we need to use. But we can also calculate the area if it's a circle by pi r squared is the area. And then the pi times a different radius would give us the other area. But we can simplify that down. There's a pi in both sides. So that simplifies down into the radius squared times the velocity. The radius of one and the velocity of that one equals the radius of the other squared and the velocity in the other squared. So that's another way we could use the equation. Radius is the same thing as the diameter divided by 2. So when I take the diameter under one circumstance and square it and square the 2, the 2's would cancel as well. You'd have 2 squared and 2 squared, so you'd really be canceling 4 from both sides. But it does simplify down to this as well. This is our base equation, and these are just simply variations. That it is, if we don't actually have to calculate the area, we can just do it in terms of the radius squared, because the area is proportional to the radius squared, or the diameter squared. So an example from sailing, if you were to sail or take a boat through this passage, and this is called Agate Passage, the channel here is pretty wide, the cross-sectional area that's pretty big, and then it tapered into a smaller cross-sectional area, but the water that flows by there every second must equal the water that flows by there every second, so it must have had a higher velocity, 3.9 knots, which is a nautical mile per hour, versus 1.6 knots. Okay. I found need to find how much air was coming into my classroom to make sure it was up to code. So I built this little device here out of foam board and put it up over the register that was putting air into my classroom. So the area of that register was 2 feet by 2 feet, and air was coming out at a certain velocity, and I wanted to calculate the cubic feet per second that was coming into my classroom. I had 4 registers in my classroom, so I had to do it for each of the 4. But I just had that taper down into a smaller area, and it's going to have a higher velocity. This is a vernier instrument where there's a anemometer. It measures the velocity of the wind, and it just displays it on the screen here. So knowing how fast the air was blowing and the cross-sectional area, I could calculate how many cubic feet per minute were coming into my classroom. So with this lab that we're going to do, the one challenge here is we would like to calculate the diameter of this hole, not from a single set of data, but a whole set of data points. Not just knowing one velocity and the area, measuring the other velocity, and then finding the area, but using a graph to do this. So area 1, velocity 1 is the area of the cylinder here, and the velocity of the water flowing down the cylinder here. The area of the hole here, and the velocity of the hole, the water coming out the hole. The challenge here is that when this is very deep, there's a lot of pressure here. So the water is squirting out very fast, shooting pretty far. But that makes the water go down. So the pressure here is going to be less after a few seconds, and the water is going to squirt out less of a distance. So what we want to do is be able to calculate at the moment the water is at this level, what's its velocity, and what's the velocity here at that same moment. To do that, we got to do a little calculus. Now this course is AP Physics 1 or even just regular physics. Calculus is not part of that. You'll get to calculus later probably. But I want to introduce you just to a little idea, but don't freak out if I'm talking about calculus. Okay? So we have talked about just regular kinematics, that we can find the average velocity. This is position and time. The average velocity between 3 seconds and 8 seconds would be the slope of the line between those 2 points. It has a change in the position over a change in time. So the average velocity is a change in the x-coordinate over a change in the time. Okay, or I should say a change in position over a change in time. We say delta x over delta t. And I could get a different average by taking the average of 2 points that are closer together, or 2 points that are really close together. This is my change in position, this is my change in time. But if I want to find the instantaneous velocity, how fast is it going right there at that instant, I have to find the slope of 2 points, like here and here, but as those 2 points get closer and closer and closer and closer together, so close they actually become one and the same point. And this is a little calculus notation, but this is just saying the limit as delta t goes to 0. As our change in time gets closer and closer and closer and closer to 0. So instead of saying delta x over delta t, we say dx dt. That is an infinitesimally small change in position and an infinitesimally small change in time. Okay, so these are like large changes, but these are infinitesimally small changes. How are we doing? I hope we're doing okay. We'll do some more examples here. But what I would like to do is, here is a graph of position and time, and I'd like to calculate the equation of how fast it's going at that time right there. We know from regular kinematics that the position is going to equal 1/2 acceleration times time squared. So we can find the average by taking the slope between a point here and a point here, but then we're going to make those 2 points get closer and closer and closer and closer together, so close that those points are one and the same. So here is the time that I want to find the velocity at. Here is a time h units away, so this is time plus h, and then we want to figure out what it is as h becomes smaller and smaller and smaller, closer and closer to 0. So to find out where on the red curve we are, we have to plug time into our function, and then to find out where this point is, we have to plug t plus h into our function, and then subtract to find the difference. All right, so the change in the position is going to be this. It's this point here minus this point here, and the change in our time is going to be this minus that, or just h. So here it is. This is our function, x equals 1/2 at squared. So we're plugging in time and then a little further away. That's time and a little further away to figure out where we are up here. And we're subtracting it from just plugging in time. Okay, and then so this is the change in x over the change in time. Change in position over the change in time. All right, now what I'm going to do is just do some algebra. There's a 1/2 a in this term and a 1/2 a in that term, so I'm just going to pull that outside. And then this term here gets squared, so we're going to FOIL that. We're going to first terms, outside terms, inside terms, and last terms. So this right here is just this expanded out, and I still have minus t squared and minus t squared. It cancels. Okay. What I'm trying to do is be able to find the limit as time goes to 0, but I can't plug in 0, or as h goes to 0. I can't plug in 0 there because I can't have 0 in the denominator. All right, so this is just the same thing now. I am going to factor out a 2. So if I factor out a 2 from this term, a 2 and an h, there's an h here and an h there, I get 2h I factored out, and I get the 1/2 here, but if I distribute it back into here and here, I do get back to that original thing. The reason I wanted to do that is because h cancels out now. I don't have h in the denominator anymore. The 2 also cancels out. Okay, so now I don't run into any problems with plugging in 0 for h. Remember, I'm trying to find the slope between 2 points that are so close together they're one and the same, as this h got closer and closer to 0. So that term is just going to become 0, and I'm just left with acceleration times time. That we say dx dt, that's an infinitesimally small change in the position over an infinitesimally small change in the time, is going to just be how fast was it accelerating and what moment in time are we looking at. Okay. Just look at this for a moment, how this is related to that. We have at here, but there's no 2 and there's no 1/2 over here. Dx dt gives us the velocity. This is what in calculus called the power rule, that if I want to take the derivative, which is dx dt, all I have to do and it's called the power rule. It works for any polynomial. You take that 2 and you bring it down in front, and then you subtract 1 from the exponent. So if I want to take the derivative of this, x to the n, I bring the n down in front, and I subtract 1 from n. So here I brought the 2 down in front, there it is, and I subtracted 1 from that, there it is, and so the 2's cancel here, and 2 minus 1 is just 1. That's the velocity. That's the instantaneous velocity acceleration times time. Some other examples of that. If we had taken our kinematic equation, not just 1/2 at squared, but the initial velocity in time and the initial position, I just did this one for you, but if I take the 1, which is of the t, and bring it down, I just get there. 1 minus 1 is t to the 0, and t to the 0 is just 1, so I'm just left with a velocity, and that term disappears altogether. Okay, if I take the derivative of the velocity, an infinitesimally small change in the velocity over an infinitesimally small change in the time, doing the same thing I just did here, it would just give me the acceleration. You'll get more of this when you take calculus, and it will make more sense, but this is all we're trying to do right here. Just some other examples of the volume of a sphere is 4/3 pi r cubed. So if I apply the chain rule, I bring the 3 down in front, it cancels with this 3, I subtract 1 from that, and I'm just left with a 2. So I get the area of a sphere is 4 pi r squared. The area of a circle is pi r squared, and the circumference of a circle is 2 pi r. So bringing the 2 down in front and subtracting 1 from the 2, this is called the derivative using the power rule. So this is going to be our lab, and so you'll go to the link in the description to get to this lab. What I have done is I took a video of this water right there and where it was on the ruler. So I'm calling 0 where it started, and then where it was every 5 seconds. So at time 0, it was at the origin. 5 seconds later, it was 3 centimeters, 0.03 meters. After 10 seconds, it was down at 6 centimeters. At 15 seconds, it was down at 8.5 centimeters. Okay, so this is just where the water is coming down here. And then I see the stream shooting out here and hitting my meter stick here. So at time 0, that stream of water shot all the way out to 34.5 centimeters, way out there at 34.5 centimeters. At 5 seconds, it was shooting at 32 centimeters or 0.32 meters, but the velocity of this water was constantly changing, and the velocity of this water was constantly changing. What I want to do is find out, by knowing the position as a function of time, I want to calculate the velocity as a function of time. So I'm going to graph the position and time. So I'm going to graph the position and time, and that's what I get. Then you can go into settings and display fit a trend line. It will be a polynomial, and then you'll show the equation as a label. So I fit this light blue line to the data, and then this is the equation that it gave me. I'm just cleaning it up here. 3.15 e to the minus 4 is just moving the decimal 4 places. So 1, 2, 3, 4. And the same thing for that. This is the equation that gives us the position as a function of time. To get the velocity as a function of time, I take the derivative. I bring the 2 down in front and subtract 1 there. And then when I take the derivative here, I just get rid of the time. That term disappears altogether. So I can figure out what the velocity is by plugging in the time to this equation. Let me come back up to here. I can figure out the velocity here by plugging the time into that equation. So that was using the calculus part. Here, I wanted to find the velocity of the water coming out of the hole. That's going to just be using projectile motion. Knowing the distance that water fell we can calculate how much time it took to fall that distance. Knowing how far it went in that time, you can calculate how fast it was traveling horizontally. So we're going to use projectile motion to calculate those velocities of the hole at these times. Then I want to rearrange this equation to make a graph, and I can use that graph to find the diameter of the hole. And I'm not going to tell you exactly how to do that. I want you to struggle a little bit with that. The accepted value will show up once you have the correct value here, once you've typed in the right formulas. But and then the percent error of difference, these cells will turn green when you type in the right formulas. I wish you the best.